Hello, good afternoon, everybody. It's great to see you here. Welcome to DevOps. I hope you enjoyed your keynotes this morning. If we can believe Stefan, then we'll get a lot more code in the world and we'll be around fixing it. Before we get started on me, why I'm here, and what we're going to talk about, I want to learn a little bit more about you, because I am a curious person, so that's why I want to zoom in to things. So I built this truemometer, and it addresses what's true for you. It measures the temperature in the room. And the first check I want to do with you is every time you hear AI, what do you want to do? Do you want to scream, impose a €1 fine, start a discussion, or start building things, just like Stefan? Now, the way this truemometer works, it may be a little bit of a challenge to you, is that we all get to stand up. Oh no, we're not gonna have to stand up. Yeah, are you ready? So stand up, and then when the truemometer is gonna rise, you sit down as it hits your mark. Now I see reluctancy for standing up, or yeah, there we go, excellent. Okay, so I hit the truemometer button, and I want you to sit down as it hits the mark that is right for you. Yes. So few of them sat down in the beginning, and I still see some of you standing up. I mean, it's too much, right, sometimes. So what I'm going to do today, you can sit down again. We'll do a few more of these. What I'm going to do today is boil down into some of the basic mechanics, math behind AI, because I think it needs to be demystified. Oh, there we go. The instructions come late. So again, what's true for you? How do you regard your math proficiency? Is it either, let's see, these animations are not where I want them to be. So let's all stand up and I'll shout out the references and you get to sit down when it hits your mark. So what's your math proficiency? Does it cover the basics? Is it high school level? All right. University grade. And then there is a genius in the room. Excellent. Great to see. Do you want to swap places? Then I can get to lay down on one of the beds here. No? All right. Let's see how the animations are going to be in this one. How much do you guys love Star Wars Lego? Nothing else on your mind? Or, sure, Star Wars, no, but Lego, yes. Nah. Now I see some standing up already, but I'm going to shout it out again. So get up. Temperature is going to rise, and whoever thinks meh can sit down. See, some of you are going. Lego, yes. Star Wars, no. Sure. And we have nothing else on my mind with the math genius. Excellent, thank you. Then the final one. Do you like Rubik's Cube, LAN parties, or 42? Well, again, it depends. All of them? Just one of these? Or see what? All right. I promise this is the last one, guys. Thank you for cooperating. So who says, say what? Yes. Just one of these? That would be me, Rubik's Cube. All of them. And yes, I must say, these are the true software developer, right? It depends. It depends. It's the answer always. Always the nuance. Well, it's obvious that I didn't select these statements just for the fun of it. They hold some biases, and these biases don't hold true for me. So I think it's always important to discover what it is that defines us, or what it is that defines our field. Now, for me, I do like Rubik's Cube. I do like Lego, no Star Wars. And my colleagues had to explain to me about LAN parties and 42. But now I get it. Now I can make the insider jokes as well. My math proficiency is decent enough. It's through my mother's line. And this is my grandfather. He enjoyed building fractals in the 80s. And I remember it took hours to render, if not nights. That was a different time from now. Through his line, one of my ancestors is IJzer IJzinga. Does anyone know the planetarium in Franeker? Yes. So he built the oldest still functioning planetarium in the world. So through my great-great-great-grandfather, I had to practice this, and my mother's line, I have gotten some mathematical interest and affinity. But as it goes with teenage girls, I took a different choice for my education. So at Utrecht University, I studied communications. It took me another 20 years to discover the world of software development. And actually only by then, I started realizing that my mother was in IT. She was a tester at IBM before we were born. And she automated everything in my father's pharmacy. But she never put that up front, and she never made it about her. Now, when I started working at the KVK in my traineeship, I discovered the fun in programming. And following the years, I got into a leadership role. For the last 3 years, I was a practice lead there. And I moved into the CIO office recently, so I'm a bit more distant from programming. But one of the things that I really like as well is my community leadership. So for JFO, who knows the JFO conference? Yes, excellent. Got a ticket? If you would still want a ticket, you can participate in the Masters of Java. It's a fun programming competition, and it will get you an entry ticket to JFAL. JFAL is one of the conferences that we hold as NLJAC, the Dutch Java community, and I enjoy a lot being a co-lead. Now, the most important thing about me is that I am curious. I am very much into discovering how things work. So that's how we get to discovering the simple math that powers AI. I think it is really important to zoom into something when it is attributed magical properties. I mean, if we listen to Stefan this morning, it's all there is gonna be. And I heard him consider it lightly to use generative AI in any circumstance. And to me, it's important that we zoom into what happens actually under the hood. So at the end of this talk, you too can spread the word that it is actually simple math powering AI's magical capabilities. So we're going to make 3 discoveries under AI's veil. 1, underneath it all, everything is binary. 2, AI's core is powered by simple math. And AI's answers are computed probabilities. We're going to earn 5 badges along the way, and we're going to move through a landscape where we discover the numerical excavation site, our floating point pond. We will rise up into the world of transformative AI. We will descend through the valley of error and loss. And we will finally arrive at our destination, the big city of interaction. So this is the route we're going to take. And let's get started on the numerical excavation site. So I want to get back to a few basics. And I understand that to some of you it may be a repetition of stuff you've learned before. But I think it's important that we get the basics right. So I'll address the evolution of numerical systems, and I'll address the basis. Who knows what this is? It's Babylonian, excellent, hexadecimal system, which means they counted up to 59, and it's one of the first occurrences of a written numerical system. It's 4,000 years old. Next came the Hindu-Arabic numericals, and in the 5th century, and this is a recording of it, they introduced the 0 as a positional placeholder, and that changed a lot. Only it took many centuries before it got introduced to Europe. Let's see how that went. So another 400 years after the 0 took root, Al-Khwarizmi wrote Al-Jabr, and he described how the Hindu-Arabic numerical system could be used in computation, in calculations. Another 300 years later, it got translated into Latin, and the name of the writer got translated as Algorithmi, and the book as Algebra. So this is where the terminology in our modern math is rooted. It took this is the first recording of a binary numerical system. Did you guys know that it was in 1703 that Leibniz wrote about the possibilities of a binary written numerical system? That's quite a long time ago. And it took another few centuries until in 1950, or 51 perhaps, we saw the first electronic binary computer called UNIVAC. It worked with vacuum pumps, and the reason that the binary system worked so well in computing is that it maps perfectly to an on-off state of things. Ever since, all computation is binary, so also our AI is rooted in these basic principles. Now, the basics of our numerical systems may also seem obvious to you, but I want to get into a few of them. So our decimal digits are rather natural and intuitive, we know them, and the positional system using the 0 as a placeholder is very known to us now. This is the way we note things. So at the right you see the first position holding the 1s, which means it is our base lifted to the power of 0, which always results in 1. Next is our base lifted to the power of 1, 2, 3, etc. And it gives us the 1s, the 10s, the 100s, and the 1000s. So the number 1011 in our decimal system adds up to 1011. Moving on to the binary system, we have only 2 digits, the on and the off state, of course, and this has the same notation but results in different quantities. So the first position holds the 1s, then the 2s, then the 4s, then the 8s. In this system, and you see how we note the binary number with the base 2 at the bottom, this will come in handy later, and it adds up 8, 2, 1, resulting in 11. Then there is the hexadecimal system. Does anyone know why we use that? Why it's here? Yeah? Want to take a shout? Simplicity of? Yeah, to write it down. Yeah, because binary numbers get large. I mean, you already need 4 digits to represent only the number 8. And for every 4 binary numbers, you can use 1 hexadecimal number. Because 2 to the power of 3 is 16, to the power of 4 is 18. Oh, God, wow. Well, let's rephrase that. So for the first position, 16 to the power of 0, again, it holds the 1s up to 15, which in digits in our decimal system doesn't exist, so we use the alphabet for that. So A resembles 10, B is 11, and so on until F is 15. Now, in this case, the powers quickly grow. So the third position is already 265 in quantity. And if we start computing with numbers, sorry, this holds an old some that is from earlier, so let's skip that. So if we use the number 1011, we need to add up 4069 plus 16 plus 1, and then we have the value for 1011 as a hexadecimal number. I'm going to scoot over that mistake. Now, getting to this point, I want to just check in with you. If you want, you can stay seated. We'll do it by raise of hands. So we start by all raising our hands, and then we get to decide where the thermometer will take us. So lower your hand as the thermometer hits your mark. All right. So I think this illustrates well that some of these basics we don't revisit often. We kind of assume that we know, and it doesn't hurt to just take a time and get into it. Now, we earned our first badge. Congratulations. We're going to move on to the next phase, which is our floating point pond. Because considering the numerical systems and how they are noted, how do we go about the decimal fractions, the binary fractions, and storing them? So again, our decimal system with these positions to our bases, but this time we raise to the negative power, which gives us fractions actually. So we get 1/10, 100th, and let's see if I get the right one, 1,000th. Okay, let's hope that doesn't occur too much more in this slide deck. So in this case, if we want to register the number 0.011 in the base 10, we add it up to, well, it's the same, of course. This is one system. If we do that for binary digits, we get the fraction 1 at the half, the quarters, and the eighth. Now, if we get to represent this number in base 2, we have to add up a quarter and an eighth, and we get 0.375. So fractions are really different in different bases. And the numbers you can represent using these fractions differ as well. How do we go about registering these floating points in our binary computing system? So we have the single precision floating point representation. Anyone here born in 1985? Yeah, you are as old as the definition of the floating point representation. Congratulations. So this is the agreement to how we store floating points. We have in the single precision variant 32 bits representing 3 responsibilities. The first bit is our sign bit. It registers whether the number is positive or negative. The exponent bit, which says to what power to raise our fraction to. Now let's see how that plays out for this number. And I'm going to challenge you. I wonder if anyone already knows what this number is in decimal. Well, let's get it more readable in the hexadecimal. Not yet. Let's see where we're getting at. So the way we compute this is we rise -1 to the sign bit, which always results in a positive value for the 0 sign bit and a negative value for the -1 sign bit. The 1 sign bit. For the exponent, we have something complicated going on. So you see that the exponent here, the bits it holds, is a binary number. We can compute that to a decimal number, but then we also need to subtract 127. The reason for that is this is what we call holding a bias. This way we can use a positive number, a positive binary number, and use it for positive and negative powers equally. So by subtracting 127, we can raise to the powers of -127 to plus 127. We multiply this with the fraction bit, lead it with 1. we get the 1 for bonus. And there we add up the fractions that are represented in the binary fraction bits. So for all the bits, we count the fractions that are involved. In this case, the half, the 16th, the 128th, and what's next. This is the sum that follows. So we get 1 multiplied by 2 to the first, which is 2, and then this number. Anyone already aware of the number this represents? Pi. Excellent. There we go. Now, we all love a bit of pi, don't we? So, which is why I want to get into the binary storage of pi. Currently, we know there are 100 trillion digits of pi, decimal digits. Now, storing 1 decimal digit takes us 4 bits, because 10 lies between the 3rd and the 4th power of 2. A byte is 8 bits, so with 1 byte we can store 2 digits of the decimal of pi. This adds up to 50 terabytes. Anyone owns a hard disk of this size? No. If you, oh, there one? No. If you could, if you did, you could fill it up with pi, and that would be it. Now let's see if we grasp this fully. So we're going to do this again with the truometer. So binary fractions and storage are still intimidating. I think I get it. So we're going to hit the truometer soon. Or nothing new for me. I'm going to get it started and just lower your hand when it hits your mark. Nothing new. Clear. I think I get it. And no one is still intimidated. That's great. Or was there one? Yeah? All right. Let's dive into it more later. I'd love to. We earned our badges again. Thank you so much. I'll take a bit of water for our next phase. Because we're going to have to climb up to the elevated terrain of transformation next. So in generative AI, we have transformators that compute with the input and deliver output. And in general, this is done with neural networks and involves vectors, matrices, activation functions, and computing with probabilities. Now, AI is a very generic term, and I actually fell into the pitfall as well of using it for anything involving stuff like this. That's as generic as it is. But I think in this case, mainly we are addressing how GPTs and LLMs work. There's a lot more to AI, but I'm not addressing that. So we're going to zoom into the inner workings of a neural network. We're going to clarify what happens inside the node. And after this, you will understand vector math, activation functions, and probabilities. Now let's see. Gen AI simplified is given some input, what should come next? In this case, given hello, should come next, world or DevOps. This is a very simplified representation, of course, and in the real world models, this is done on repeat and on steroids all the time. And I think by the end of this talk, you get a gist for the massive computation that is underneath. And consider that every token that is produced by generative AI requires a lot of computation. Now, I'm going to use the word token a lot. In this case, it means the set of around 4 characters which hold all elements AI needs to produce text. So it doesn't hold a vocabulary as we know it with full words containing meaning, but it holds building blocks that it can use to form any word. Who is familiar with this kind of image? Perfect, yeah. So this is generically what a neural network consists of. So we have the input layer where the input token is fed into. Then that knows an embedding dimension. We'll get into that a bit later. It outputs something associated with the vocabulary size it holds. And in between are the hidden layers where the computation is done. Now, let's see what actually gets fed into the system. This revolves around vectors and dimensions. So, given the input token hello, which would probably not exist in the vocabulary as a token, but for simplification, we'll consider that. In this case, it has an embedding dimension of 2. That means the system knows 2 features of this token. And in real-world models, these numbers are massively higher. But for simplicity's sake, I'm going to address it with a 2-dimensional vector. Now, why vectors and why these dimensions? So this enables AI to compute on text using numbers that still get to represent the intricacies of our natural language. It gets to represent many features that our language holds. This is the notation of a vector. We're going to see quite a few of them. So it's the x with the arrow above, and then the x1 and x2 are the components or features of a vector, and it's generally noted as in this way. Whereas in computing sense, I would say it resembles an array, right? So why go hard with writing them underneath? But in general, in math, this is how it's noted. Now, what happens to actually get from hello to a prediction for world or DevOps? The first thing that happens in the input layer is the token lookup. So somewhere in a vocabulary, it holds the relations between a token set of characters and the vector of features that is associated with this. We will assume for the further topic that this has been done. So it results in a vector, in this case of 2 dimensions, and that gets fed into the first hidden layer. In this layer, every node applies a computation which transforms the original vector into a vector of the size of the nodes, in this case 3. So every node computes to 1 scalar number, and together the layer produces numbers in a vector the shape of the neural layer. So the number of vectors corresponds with the number of nodes. Now, after the final layer, we need to map these vectors to the vocabulary size that we're working towards. In this case, the vocabulary size is, again, very limited, only 2. But a different computation happens in this final layer. And as we get these final logits, as it's called, we need to move to token selection, which is similar to the token lookup, but reversed, and it actually happens outside the neural network. All right, so let's get into some of the details. I'm gonna explain first what transformation happens inside every node. Now, every node in a layer contains a weight vector, a bias. They take the input vector and produce a scalar number. And it uses an activation function in the process. Now consider weights, like the importance this node gives to each feature of the vector. So every node holds a set of weights for its own. The bias is more or less a personal inclination of the node to render a specific value. So even if the result of the weight factor computation on the vector is close to 0, it can still add the bias to it and produce it as a signal next. So the formula that is used to describe this, and here you can see, I mean, math is essentially a very concise language. It just says in the right what is written out in the left with a few extra computations. So in each and every node, we see this happening. The input vector gets multiplied with the weight vector. The bias is added, and to that, an activation function is applied to get one scalar number. Now, why activation? So this is a concept that is really essential to generative AI, and there are several ways of explaining it. and they hardly any of them do real true value to it. So I'm going to try to explain it intuitively. These are 3 examples of ways activation functions transform the value of the computation that was done between the brackets. And what it does is that it moves from a linear connection of the input to the output to a non-linear connection. And that resembles the natural language much better, because we don't have only linear connections in our language, which is why we need to break linearity. And there are many mathematical formulas to do so. And part of the success of LLMs is depending on the functions they use. So ReLU, as you can see, is one that is widely known, and it just flattens out the negative values to 0 and processes whatever comes as a positive integer. Then hyperbolic and sigmoid are some others that are well known. I'm not going to dive into their formulas because this is supposed to be an unintimidating talk. Now then, what happens in the final output layer? So this is where we need to map to the output size of our vocabulary, which is 2 in this case, whereas we get an input vector from the previous layer of 3 components. Now, this node holds a weight matrix, which is 3 by 2, so that we can use it for computation to produce a 2-dimensional vector. Again, this is a multiplication between the weight matrix, in this case, the input vector from the hidden layer. Added is the bias vector, and we output the logits. Here we don't use an activation function because we are connected to the final vocabulary. Now, what does this look like? And this is essentially the most mathematical slide in my deck. The formula can be computed with a given weight matrix, a given input vector h, and a given bias of 2 values. Now, this is what happens inside the final layer. We multiply the weight matrix, giving relevance to every aspect of the vector. And we do that simply by multiplying each column of the matrix with each value of the vector. So here you recognize that reading from left to right, we see the first column introducing the first number of the input vector, the second, the third, the third. And we see that the matrix moves from left to right with 2 rows and 3 columns. Now this results, it's really as simple as plain multiplication, but just positioned into this matrix, and it gives us a sum resulting in minus 1.7 and 2.3 for the values used here. After that, we need to add the bias, and that is just a simple addition. That results in our final logits, minus 1.2 and 2.1. Does this feel hard or easy to you guys? So hard, let's point to this way, easy to that way. Yeah, okay, there's more there, but there's a few there. I think it's good to be honest about this. And to me, of course, I've had a process getting into this and getting a feeling for this. I think the essence here is that with a set of numbers represented in a hierarchy or in a grid, what happens underneath is simple multiplication and addition. And we all learned that in primary school. Now, if we have our logit of raw scores, do we already have our next token prediction? We actually don't. We still need to, and with 2 numbers it feels a bit silly, but we still need to make a probability distribution. And in a probability distribution, you want the numbers to add up to 1. You want to scale them in such a way that they're all between 0 and 1, and they add up to 1, which is kind of like the percentage of how probable it is that something will occur. Softmax is one of the formulas used to do so. Now, this sounds complicated, but what it actually does is it magnifies the numbers in a logarithmic scale. So that enhances differences. So if there are only small differences on a basic level, it enhances these differences. That gives us numbers that we can scale to the full addition of all values and giving us a subset that adds up to 1. And in this case, we have a probability distribution of 0.04 for one value and a staggering 0.96 for the other. So what's it gonna be for the token, right? We know enough now to predict our next token. And it's actually hello Devox. This is done on steroid, on repeat, all the time, continuously, with a lot more dimensions. But basically, this is it. Considering that, I want to know again what's true for you. So vector math, activation functions, probabilities, it is still intimidating, a little more understandable. I think I get it now, or nothing new for me. So let's raise hands. And oh, there we go. The thermometer hits nothing new for me. Think I get it too. Still intimidating. I'm glad no one is intimidated anymore, and we've earned our next badge. Excellent. That means we're going to move into the valley of error and loss. Now, this is addressing the training and optimization of the model. Oh, that's an interesting L I see there. It's interesting, right? This exclamation mark has no meaning here. It just is a typo. And here we are not intimidated because we understand what's underneath. But in math, if we see a symbol that we can't fully comprehend, we tend to get intimidated. We're going to discuss error and loss and gradient descent because in the training of the models, everything starts off random. And the model needs to learn from mistakes. So for the first time, if the weights and biases hold a certain value that has no reference to the actual output yet, it gets told whether the answer is good or not. And in this case, if the answer should not have been Devox, but it should have been world, it gets fed back into the system, this error, and the system learns, adjusts the weights and biases, and computes it again. Now, error is mathematically notated as such. It is the difference between the actual output and the expected output. Nothing magical about that. We raise it to the power of 2. We square it to both get only positive numbers and enhance errors, enhance differences. Next, we sum them all up. So this is a very common notation of on repeat, on steroids, do this for all the errors that were produced in the system. And together, they deliver, and added them all up. We divide them by the number of parameters that we calculated with the number of errors that we computed. And this together is our mean squared error. And this is what loss means for a model as such. So given all the outputs, how much error was on average in there. Next, we want to know how weight impacts this loss. And this can be represented in a graph. So it resembles how much the loss changes as the weight changes. I'm using a hyperbole that is not very complicated here. We all remember those from high school. Imagine that this one holds 2 dimensions, but in large language model, we hold many more dimensions, and still the process is the same as this. So if given a certain weight, we're going to see how we should adjust the weight to lower the error and loss. This is called the gradient. So the gradient is the ratio between loss and weight. And to improve the model, for the next training round, we're going to take a small step towards the minimal loss, which is at the bottom of the graph. And this is called the gradient descent. So for every training round, again and again, this is computed to reach the minimal possible loss. Now, this graph has an extra dip to address an issue that rises from this. In this case, it did find the actual minimal loss to the model. But it can be that you fall into one of the other local minima, as it's called. And this is a very challenging topic where you need more advanced math, but still it boils down to finding a way to getting to the bottom of a hyperbola. And again, this is done on repeats, on steroids, all the time, continuously, during training. The term epoch is every step along the way. Every training round is called an epoch, and you can see online how many epochs is used to train a model. Now, this is it for optimization. So what's true for you? Model training and optimization is still intimidating, a little more understandable now. Can it be this simple? Nothing new for me. So raise your hands and lower it as the trumometer hits your mark. So we do get, yeah, I think I saw quite a few lower at can it be this simple? Is that true? Hold hands for it can't be this simple? Oh no, so that was one of the other marks. Basically, this is what happens on steroids, on repeat. Congratulations. This was an easy batch, right? This was not the hardest. We're ready to move into our big city of interaction, because having the trained model and understanding what happens in generative AI, do we now know enough and have enough to start making money and put our model into the market and get Stefan going on it? I'm not sure. We have to address the number of parameters in models, quantization, and model size. Now, for the example we used, we had only 2 layers, 3 nodes per layer, an embedding dimension of 2, a vocab size of 2, and that gives us a total of parameters, so the weights and biases in every node, of 29. That's not too staggering. Now, GPT-3. And we're now at GPT-5, right? So I understand that the numbers have been computed, have been published up to 3, and after that we are guessing, which is why I refer to GPT-3. It has 96 layers, each holding approximately 32,000 nodes, with an embedding size of 12,288. So these are the features of the tokens that are fed through the model. And it has a vocab size, all the tokens, of 50,000. The number of parameters in GPT-3 is around 175 billion. And we remember how much it took to store these numbers, right? So if you imagine how much storage is needed to do that, it's impressive. So we need to get to quantization. And quantization means that we squeeze our big floating point numbers into a cheaper, smaller size. And it's a rather simple process where we measure the scale of the numbers that we need to represent in adherence with the level of variety we have in our new data type. In this case, we see a scale of 127, the maximum value in our integer, signed integer, and 7.8 is our absolute max, highest value. So this is the abs max quantization. There are different types of quantization, but this is one of the ones that is being used to do this. Now, if we quantize a 32 floating point number to int8, that gives us a 25% compression. So given the 175 billion parameters, which each held 4 bytes as FP32, we move from a 700 gigabyte model to a 175 gigabyte model. That's already quite a big improvement, but is that enough, or do we need more? As we quantize further, which we can do, we can limit the model size, but still we need to consider that the number of parameters simply hurts performance. And quantization hurts accuracy, because you can only imagine that quantization already hits, I think it's even below 2 bits, so the Q8, Q4, and Q2 means to what bit size it's being quantized to. And it's important to, if you don't want to lose accuracy, to use mixed precision. So this is something models do, where they say, well, some of the parameters are not as critical as others, so we discern between the parameters that we will quantize and the others that we won't. Now, getting to this point, again, what is true for you? Model size, performance, and accuracy is still intimidating or not? Let's see. Perhaps it's not even new to you, can't be this simple, or yeah, okay, so that's what I figured. It really is this simple. So excellent, well done. We earned our last badge, perfect. Now let's see where that takes us. We zoomed in on the numerical basics, our floating point precision. We walked through the elevated terrain of transformation and descended through the valley of error and loss to arrive at our final city of interaction. Is there nothing more to discover? Well, we still have some other uncovered terrain, of course. I mean, you're gonna hear about a lot of these topics these days, possibly, or maybe not even the details behind AI, but more the application of it. But I think it's important that with everything you hear, you will be willing to discover what's under AI's veil. Remember that everything underneath is binary. At its core, it's powered by simple math. AI is a lot of computed probabilities on repeat, on steroids. You've earned your badges, well done, and thank you so much to my sources, and thank you for your attention. And getting to interaction, we have some time for questions or remarks. So is anyone interested to raise a topic? And I know it is intimidating to do for a full room, so if you want to come up to me, that's fine as well. Thank you.